Hi, welcome to my latest video about the volume, in particular volume of a pyramid. Look at this picture of the Caffrey pyramid. What can we say about it? It's large, of course. There are the dimensions. It's actually square based of approximately 216 meters length and width, and the height is about 136 meters. What we are interested in is what its volume is going to be. How can we work that out? If you've studied the topic of measurement, you might have come across the formula for the volume of a pyramid. What's the formula? There it is. The volume is a third times the length times the width times the height. And if we use the values that we have, the volume comes out to be approximately 2,100,000 cubic meters. Quite a lot of space there, isn't there? That's well and good. It's very easy to apply a formula that you're given, but more interesting is where does that formula come from? I'm going to show you how I developed the formula using layers of areas, as you'll see in the animation following. Here is the pyramid. The way we will obtain the volume is to create cross-sectional areas that consist of rectangles and then summing them to obtain the total volume. And of course there will be an infinite number of these rectangles. Here's a visual demonstration of what I mean. We have the rectangles at each height, and summing them we get to the top, and the volume is increasing, of course, and the total volume is about 2,115,000 cubic meters, based upon the dimensions of the pyramid that we had earlier. The problem now is, of course, how do we sum those rectangles to infinity? Now let's see how we develop that formula. Here's a diagram of our pyramid. We have the length and the width. We're going to keep it general, so even though our pyramid originally was a square base, we'll call it a rectangular based pyramid. So we have L for length, W for width, H for height. And remember, we're going to be summing layers of rectangles until we get to the apex of the pyramid. And here's a bit more detail. We have our base, length times width for the area, and at a certain point we have another cross-section rectangle of length X and width Y. And at that particular point, the height of the layers is lowercase h, and that means the remainder is capital H minus lowercase h, as you can see there in the diagram. We're going to use that information to obtain some relationships. And to do that, we're going to create what we call similar triangles. Look at how we've constructed two similar triangles. That means one right-angled triangle inside a larger right-angled triangle. And here's another way of looking at it. On the left we have our similar triangles, and in more detail on the right, the small triangle has base x over 2, and the base of the larger triangle is of length L over 2. And of course we also have the corresponding heights for those two triangles. Capital H minus little h for the height of the smaller triangle, and of course capital H for the larger. Now, what are the properties of similar triangles? Similar triangles have the property that the ratio of corresponding sides is the same, and this is what it means. If we choose the corresponding sides for the bases of the two triangles, the smaller one is x over 2 and the larger is L over 2. And if we then choose another pair of corresponding sides, let's say the vertical parts of each triangle, we have capital H minus h over capital H. According to the property of similar triangles, those two ratios are the same. Now, just simplifying that expression, we obtain that x is equal to L bracket h minus h over capital H. That means we have an expression for the value of the length of the rectangle at any height h. We're going to obtain a similar one for the width y by constructing similar triangles as well. There we are. This time we're going to use variable y to obtain our similar triangles. And just to show the working, we will obtain the ratio of corresponding sides in exactly the same way. So we have a half y over a half w equal h minus h over h. And simplifying that, we have our expression for the width y, as you can see there. So now we have an expression for the width and the length of the rectangle at any point on the pyramid. Now remember, we are trying to add all of those rectangles together until we get to the very top. So there's our rectangle, length x, width y, and just replacing those with what we found, we have what you can see there on the right. Now what's the area of a rectangle? It's length times width. There we are, x times y, or using the expressions we have, and that simplifies to LW bracket h minus h all squared over h squared. So we have an expression for the area of any rectangle on that cross-sectional part of our pyramid. How does that help us? Because remember, we are trying to sum an infinite number of rectangles. And this is where we must appreciate what we know as integration. Integration means summing. You might have done this topic. So to obtain the volume of the pyramid, which is the sum of all of those rectangle areas, we're going to use the process of integration. And here's the expression we will use. V for volume is going to be the integral of, and we are going to sum the rectangles beginning at the base, which is little h equals 0, going all the way up to little h equals capital H to the top of the pyramid. And of course, what are we summing? We're summing the areas. And that's the expression that we have there, that we found previously. Now we need to know how to integrate that expression. Firstly though, to make it a bit easier to work with, capital L, capital W and capital H are all constant. They are given fixed values, so we can put those to the front as shown there. And now it's just a matter of integrating what we have on the right, which is bracket h minus h squared. And just using our techniques for integrating or anti-differentiating, that's what we obtain. You add 1 to the power and divide by the power. And also there's a negative in front, which comes from the variable h, little h in the bracket. And we are, of course, integrating between 0 and h, as shown there at the end of those square brackets. Now what that means, of course, is that we replace variable h with capital H firstly, and then 0. And with a bit of manipulation, simplification, first of all replacing with h, and then 0, and then simplifying some more, we obtain the formula that we started with, which is a third LWH. Now just to finish off, let's look at it in another context. If we draw our pyramid circumscribed by a rectangular based prism, or a box shape if you will, like that, what's the volume for that prism? It's LWH. And the volume of the pyramid is a third LWH. What is the connection between the two solids? Well, it's not hard to see, is it? That the volume of a pyramid is actually a third of the volume of the rectangular based prism. I hope you've appreciated this novel way of working out the volume of a pyramid. Go back and pause the video to make sure that you understand the calculations involved. And if you have any comments, please let me know. Until next time, bye bye.